With our next speaker, John Guoynes. John is the Vice President of Business Development for E3 Energy Services, a compression and midstream service provider. John has over 30 years of experience in Appalachian oil and gas, including Director of Production at Rice Energy and Energy Manager at CNX Gas. He has experience in the upstream and midstream sectors of unconventional and conventional plays, including production, midstream facilities, reservoir, CBM, gas storage, and enhanced oil recovery. He is currently involved in developing new technology for oil, natural gas, and NGLs, including new and practical solutions for lowering our carbon footprint. John is a graduate petroleum engineer from Oklahoma State with an MBA, has authored numerous publications and served on oil and gas committees, including a previous appointment to a state oil and gas regulatory board. So please join me. Welcome, John.
Thanks, Drew. Before I talk about E3 Energy, I thought I'd bring up what should be the number one question on everybody's mind. I'm surprised nobody has brought this up yet. Who is going to be the number 20th pick tonight? Now, for those of you who are football followers, and especially Steeler followers, whoever number 20 is going to be playing for the Steelers. And probably replacing Big Ben. And just a side note, I was talking to my daughter the other day. She's a PGA professional, and she is in charge now. She took a new job. She's in charge of the PGA Junior League system for the tri-state area, which is Ohio, Pennsylvania, and West Virginia, and also the mid-continent, which goes all the way over to DC. And I saw the roster of this area's PGA Junior League, and there's going to be a couple of mini bins on the PGA Junior League roster. So that's kind of interesting, I thought. So I'll tell you a little bit about E3, what we do. We are a midstream and compression services provider. We have done and do build, own, and operate, where we own the equipment, build it, engineer it, design the whole system, and then we operate the midstream facilities. We also do compressor leasing and facility leasing, and we're based in Dallas, Texas, and we have primarily been involved in the Northeast here over about the last 12 years. Built a lot of things for Pine Run, Penn Energy, Antero, several companies. Eclipse was one of them that we did work for. So that's who E3 is. And I want to talk. We're not moving. Let's see. There we go. I pushed the wrong button. Okay. So I want to talk a little bit about what companies are doing to address their net zero carbon standards right now. And a group of investors representing about $10.4 trillion set new standards for oil and gas companies. And the reason they did that was because a lot of companies developed their own standards, their own guidelines, and there was a lot of inconsistencies and no way to really judge how companies were doing because they all had different standards and goals. So these investors set these new standards, which include short-term and long-term net zero targets, decarbonization strategies, capital allocation and disclosure and reporting. So they tried to standardize some of these things so that companies like ExxonMobil's and Bechtel's and EQT's and these type of companies could all be ranked similarly. And what's happened now is many companies are targeting to be at net zero by 2050, some even as early as 2030. So that means they're trying to reduce their carbon emissions. And the Greenhouse Gas Commission has defined 3 scopes of emissions. There are Scope 1, which are direct emissions, which are produced by the company. Scope 2 are indirect emissions, and these come from things that they use or are generated in the purchase of energy. And then Scope 3 are indirect emissions that are not owned or controlled by the company. So what is important about that is most companies are focusing right now on trying to reduce their Scope 1 and Scope 2 emissions, those they have direct control over and the ones that they have indirect control over, things they buy, use, things like that. So that's really where the focus is, and that's important to keep in mind as I move forward in the presentation. Carbon capture, utilization, and storage. There's really two categories. There's CCS, which is carbon capture and storage, and there's CCUS, which is carbon capture, utilization, and storage. Now, the difference is you capture all this carbon emissions and you store it, you put it in the ground, you put it somewhere where it's no longer an environmental threat. And utilization revolves around, you've seen things on hydrogen, on trying to reduce carbon footprints. Utilization might mean they're using it for an EOR application, or you're transporting it to a market that can use CO2. So those are two general classifications. And one of the ways you can get rid of carbon emissions is to put them in the ground. And you can put them in the ground for enhanced oil recovery, or you can put them in the ground permanently for sequestration. And if you look at the map that's on the bottom right, that shows the CO2 pipeline networks that are in the United States. And what's interesting from that is they're all in West Texas. That's where most of the EOR work is being done, or in Louisiana and western Mississippi. We don't see any of those in the Northeast. So why is EOR not a big factor in the Northeast? Why are people not using it? One of the fellows here that gave the earlier presentation said there's some interest in EOR applications in Ohio, in the Akron area. Probably Clinton Oil, I'm assuming, is where that is. But there's not a lot been done. Well, you don't really have a source of CO2 up here for EOR applications. That's important because as we look at how to decarbonize our operations, we're going to be generating a lot of CO2 and we have to have a place for it. Where do we put it? So in the U.S., the map on the left shows where the carbon capture potential is. These are oil wells in the green in the United States. We have a lot of opportunity to put carbon in those depleted oil wells. And if you look at the graph on the right, everything that's in blue, there are, where's my numbers? 500,000 wells, over 500,000 wells in the United States, and that are producing under 15 barrels of oil per day. That's everything shaded in blue, dark blue and light blue under that graph. So the majority of the oil production in the United States is producing less than 15 barrels a day per well. You know, a few years ago, we almost called those stripper wells. I think 10 barrels a day was the limit for stripper wells. I'm not sure what it is now. So there's a lot of application in oil recovery to use CO2. And that's a place that we can put these emissions in the ground. Carbon capture projects for CCS in the United States are shown on the map on the left. And you see there's a lot of potential, the map on the left is showing underground natural gas storage. These are existing gas storage fields in the United States. They're permitted, they're developed, they're used yearly. Gas is injected and withdrawn annually in most of those fields. Now, if you look at the map on the upper right, these are areas where carbon capture system is being looked at for storage. And if you look at those dots, the yellow circles, they're all in the Illinois Basin area. And now if you go back and look at the map on the left, those are all blue dots where those are. Why is that? Those are aquifer storage, not gas storage fields, they're aquifer reservoirs. So that means, you know, for lack of knowing any better, I guess, all of the work that's being done on trying to put CO2 in the ground is being done, the majority of it is being done with aquifer reservoirs, as opposed to looking at natural gas reservoirs which are already in existence and permitted exactly the same way the aquifer storage reservoirs are permitted. So there's an opportunity there in the Northeast, if you look at all those brown dots, which are depleted oil field storage reservoirs, that we have to put away CO2. One other graph I'll show you on the bottom right. This gives you an idea of what the cost of CO2 sequestration, CO2 storage is. And you can see it ranges anywhere from high of $35 upwards to close to $100 a ton. And that's where some of these incentives for getting rid of CO2 are coming from. Right now, with the tax credits, we're at $35 a ton for EOR and $50 a ton. Those are tax credits you can get for CO2 storage. A lot of that's coming from the cost of what it takes to remove the CO2. And I'm going to show you some systems where the costs are much lower and they're using practical, very similar applications to what we've used in thousands of facilities in oil and gas already. So one of the things I want to talk about is what's compression's role in carbon emissions. Compression is a large contributor to greenhouse gas and CO2, as well as fugitive methane. If you look at the pie chart, reciprocating compression emits about 30 million tons of CO2 a year, and this is coming from the EPA Greenhouse Gas Reporting Program. So typically a 15,000 horsepower compressor station will emit about 73,000 tons of CO2 annually. Technology is in place that can be utilized to reduce these carbon emissions and the fugitive methane emissions. It's not something new that we have to invent or develop. This is already technology that's in place that can be utilized and applied by our industry to reduce the CO2 footprint. For fugitive methane, well, let me back up just a minute. For decarbonizing compression, the most practical, common way to do that in the industry right now, what everybody's looking at doing, is electric conversions. Now, there's a lot of problems with electric conversions with natural gas compressors, especially at compressor stations. The other way to do this is exhaust capture. And exhaust capture has been available since the 1970s. It was developed to get rid of NOx and SOx emissions, and there was technology developed to take existing exhaust from internal combustion engines or other methods, burners, and capture that exhaust and remove NOx and SOx. Well, we've come up with some systems to adapt that and be able to take the CO2 out of the exhaust. And I'll share that with you here in a little bit. The other thing is fugitive methane. And it's very simple technology. There's been a lot of work done on seals and sealing mechanisms to reduce fugitive methane emissions. But one of the things that we do offshore, and we do it routinely, is we put a bolt-on capture system on compression when it's offshore. And that bolt-on system, like you see in that picture right there, captures the leakage. And the reason we do that is because you don't want H2S to be able to escape and get on an offshore platform. H2S is heavier than air, so it usually goes lower. So you have a safety issue when you're running compression offshore. So you put this bolt-on application there, and you capture the emissions from the compressors. This can be used to capture fugitive methane, and very simply, very easily can be used. So again, for decarbonizing compression, the most common method is to convert to electric. This only provides you with scope 1 emission reductions, not scope 2 or scope 3, only scope 1, because you're converting an existing internal combustion engine to an electric drive system. You do have lower maintenance costs. People say, well, electric compressors are much lower cost to operate. We love electric compression. Well, when you look at the cost of the electricity and the fact that you get charged intermittently based on peak usage and non-peak usage, the cost to operate those compressors is much higher than it is to operate natural gas drive compressors. So that's a big factor. The other factor is you have to get electricity to the site where you have compression. That's not always easy to do. It's not always fast and reliable to do from the utility companies. So that's another issue that you have to deal with. So bottom line is converting compression to electric drive is more expensive on the operator, and it only reduces scope 1 emissions. And right now, you get no tax credits in doing that. So let's look at exhaust capture. If I can capture the exhaust of my existing internal combustion engine and on the compressor, and I can maybe capture the exhaust off my generators and anything else I'm burning. If it's an oil operation, I've got oil burners out there, and I can capture all of this exhaust. Now I'm reducing scope 1 and scope 2 emissions. That's also eligible for 45Q tax credits. I have to figure out how I'm going to get rid of that exhaust or CO2, and I'll talk a little bit more about that as we go on. But CO2 can be used in a variety of applications. It can be used for EOR. It can be put in the ground for storage, disposal, or sequestration. One thing to note about exhaust is the exhaust contains about 80% nitrogen and about 10% CO2. The other 10% is water, so you have to handle water volumes. That's something that you have to do on exhaust capture applications. But mainly you're capturing 90% nitrogen and 10% CO2 once you get rid of the water. The exhaust is also eligible, as I mentioned, for 45Q tax credits. The CO2 portion of that exhaust is eligible for 45Q tax credits. So a 3,500 horsepower compressor will also produce about 1 megawatt of power from the waste heat. So not only can I capture the exhaust, I can take out the CO2, I can get tax credits for taking out and disposing of the CO2, and I can generate on every 3,500 horsepower that I have about a megawatt of electricity that I can use or resell in the process. So this is just a much more practical solution to our industry than trying to convert everything to electric. And when we start running all of our natural gas compressors on electricity, what are we doing to the power grid? We're putting a new strain on it, right? We haven't thought about that. great to have electric, but, you know, it's like, I think California had an issue on power, and they told people they couldn't charge their Teslas in their cars. They had to go on charging schedules to charge their cars. So, same thing can happen if we convert all of our compressors to electricity. E3 has developed a new process to capture exhaust. This is a patented process. We just patented, applied for patent on this. And what we're doing is we're taking the exhaust from any source. In this case, this is a typical 15,000 horsepower compressor station. So we're capturing the exhaust, which you see in the purple, and we're moving that to a rotary separator, and we're taking the water out in the rotary separator. Now, realize that exhaust is coming out at about 1,000 degrees. Remember, the exhaust contains nitrogen and CO2. So as we go further through this process, we can expand and contract the exhaust, and we get nitrogen out of that. That's processed in the end. That nitrogen is used to go back and cool the exhaust. So we're actually using the nitrogen that we're expanding and taking out of the exhaust to go back as a cooling loop to cool the exhaust when it comes in. The CO2 itself, which you see with the little green arrow, I can't point to anything here, sorry, comes out at about minus 40 degrees, sorry. And that CO2 comes out as a liquid at as much as 3,000 psi. So now you've got CO2 extracted in this process, and the CO2 is coming out at high pressure and in a liquid form. So now you can move that CO2, you can truck it, you can put it in a pipeline, you can inject it in the ground, you don't need a compressor to do that. And it's coming out in this process. What you see in the yellow is a system called a Brayton cycle, and that is generating electricity from the waste heat in this process. So this system will take the exhaust, it'll extract the CO2, separate the nitrogen. The nitrogen can be used for cooling, and also the nitrogen can be vented to atmosphere, the excess nitrogen. And in that process, we're also generating electricity. So we're generating on a 15,000 horsepower system about 1.5 megawatts of excess electricity. We're actually generating about 6 megawatts of electricity in this whole process, but close to 4.5, 5 megawatts is being used in electrical applications in this system. Now, what's very interesting with this design is it fits on an 8-foot by 20-foot skid, about the size of a compressor. So this is new technology. We really developed it from a lot of existing technology, just reapplied some of it. But we think it's very useful as an opportunity and a process to decarbonize compression in the industry and other things besides compression. Again, here's the small footprint. Used to, you would have to do this with an amine plant. You could do it with an amine plant right now. Essentially get the same results, the same thing. You might not generate electricity, but you could certainly process out the CO2, but you're gonna need a much larger footprint to put an amine system out there to handle the volumes that we're talking about with this system. And the nice thing about this, we're doing work with Southwest Research right now to test this operation and look at the purity of the CO2, but we think we're gonna end up with about 99+% CO2 in this system, so it's a very pure CO2 end result from this process. And this is what that would look like at a real 15,000 horsepower compressor station. So you could capture 100% of your exhaust. You could take out the CO2. Now you have to have some place for the CO2 to go. You could truck it as a worst case scenario. But this would take care of all of your decarbonization on a 15,000 horsepower compressor station. I'll talk a little bit about the 45Q tax credit. And there's been a lot of evolution in the 45Q tax credit. In January 2021, some things changed. And one of the things that changed is the minimum requirement that makes you eligible for the tax credit. And now that's 25,000 metric tons a year. So when you look at that process of the exhaust capture system that I showed you, the 15,000 horsepower compressor station system captures about 73,000 tons of CO2. That can also be used for turbines as well as reciprocating compressors. And so a Taurus 60 turbine compressor is going to generate roughly, the CO2 levels are lower in that than they are for internal combustion engines with reciprocating compressors. But it's going to generate roughly about 25 to 30,000 metric tons a year. So that still applies for one Taurus compressor, would still be applicable for 45Q tax credits. And the 45Q tax credits right now are at $35 a ton for enhanced oil recovery applications. So if we inject that into oil wells for enhanced recovery, you get a $35 a ton tax credit. For sequestration, where we put it in the ground permanently for disposal, maybe we convert a storage field to disposal of CO2, you get $50 a ton per credit. And that $50 a ton equates to about $4, if my math is right, my memory's right, about $4.80 an MCF for that CO2. So kind of picture converting a storage field right now where you're making maybe, 20, 30, 40 cents an MCF to store gas, and now you can make $4.80 permanently to put CO2 in place of that natural gas. It might make sense. The process that we developed is under $30 a ton total cost to remove the CO2. That's what that will cost in this application. Now, as you look at, that's for a 15,000 horsepower reciprocating compressor type application. If you go to something that has lower CO2 volumes, those numbers go up a little bit. So they may go to $35 a ton, maybe as high as $40 a ton, but you're still getting minimum of a $35 a ton tax credit to remove that CO2 in an EOR application. So we think this has a lot of application in the Northeast for sure, because remember, EOR hasn't been actively used here because there really hasn't been a good, cheap source of CO2, and it hasn't been economical. Now, if you look at it from a tax credit application and the new technology, this is a comparison using the 15,000 horsepower model on the left. The blue bars on the right are compared to the gray bar, which is the cost of operating a compressor with electricity. And the orange bar on the left is the cost of operating a compressor with a natural gas drive engine doing nothing to it right now. So that's what our typical operating costs are for compression. So now if you apply the tax credit and the exhaust capture decarbonization, we're at about the same or maybe even a little lower cost than what it's taking to operate the compressor right now when you apply the tax credits. Now, if you look at that from an EOR application and you're buying CO2 from a source, there's no comparison. The two bars to the left are the cost of EOR and the cost of that EOR application based on buying CO2. So the white bar that's stacked on top of the orange and the gray bar is the cost of the CO2 per MCF. So if you look at the cost of injecting exhaust versus buying CO2 for an EOR application, it's much lower. Now, you might ask, well, can I get the same results, or what kind of results can I get if I injected exhaust gas instead of straight CO2? Well, there's really two, other than water floods, and there have been water floods up here in the Northeast, and there's still some in operation in Ohio and West Virginia. And there are two primary sources for EOR application. One is CO2, and CO2 is used because CO2 is miscible in hydrocarbons. That means it kind of takes the place of the hydrocarbon molecule and releases more hydrocarbon molecules from the formation. So that's why CO2 is commonly used for EOR. The other thing that's used for EOR, though, is nitrogen. And nitrogen is used in a situation where you want to add pressure support to an oil-producing field. So nitrogen works very well to add reservoir pressure support. The CO2 adds miscibility. So now we're putting a combination in this exhaust of nitrogen and CO2. And if we capture additional CO2 and we apply E3's thermal technology to remove the CO2, now we can adjust the concentrations. We don't have to do 90% nitrogen, 10% CO2. We might do 30% CO2 and 70% nitrogen, because now we can put more CO2 by blending more CO2 into the system, we can increase the concentration of CO2. So we have some flexibility doing it with this type of system. And if you look at the cost, it's very economical for an operator to run this. So just in review, I'll finish up here and then we can have some questions. Interest in decarbonization obviously is growing with many oil and gas companies. Electric drive retrofits are great, but they only reduce Scope 1 emissions. They require capital support to replace engines, and they increase operating costs when you factor in electricity. The electric installation and operating costs are high, and they vary based on usage. So you don't necessarily have a fixed electric cost if your usage varies. And there's no tax credits currently available for electric conversions. Exhaust capture, we think, is a very effective and economic, practical solution to decarbonize compression and other systems. The exhaust can be applied in many applications for CCS and CCUS. And the CO2 from exhaust can be separated and transported and it can be used in different markets, or it can be injected underground for EOR or sequestration. Exhaust capture compression reduces both Scope 1 and Scope 2 emissions, and it qualifies for 45Q tax credits. Carbon capture needs to be directed at the source of the carbon, the CO2, not at our atmosphere. I've seen a lot of companies working on plans to suck in the air and take the CO2 out of the air. That is extremely costly to do. If we go after the source, we're being much more efficient and much more cost-effective doing it that way. More carbon capture solutions. The industry needs to focus on small and medium-sized projects. You see all these grants and funding opportunities out there that DOE is putting out. They're all for these big, huge, massive power plants. And they're trying to take CO2 out of these big power plants. Well, let's make something that smaller operators, smaller companies, mid-sized companies can use, that all of us can use, that we don't have to be a billionaire to go out there and develop. So if we have something that's small and cost-effective, then we focus on the volume of all these applications. Smaller compressor stations, smaller exhaust emitting applications, and I think it's a very practical way to handle the reduction of CO2. With over 1,700 midstream compressor stations in the U.S. right now, exhaust capture can provide a significant resource to reach net zero without putting higher demand on our electric supply. And that's something that we really have to take into account. And that's all I have. Any questions?
Any systems installed or pilot projects yet?
We are working with one independent in North Dakota to do an EOR application with exhaust capture gas from a compressor. And we're talking to several people in this area about larger compressor stations.
Your bolt-on capture system for the offshore stuff, is it you're just taking all your vent drains and sending it to a tank, or what is it composed of?
Yeah, it's a tank that bolts right on top of the compressor.
So it's just basically like a Jacko pod or something that you're putting everything into?
Yep.
And then from
Then you can return it to sales.
Okay, all right.
Yeah, it's really a bolt-on application, so it's pretty, I don't want to say it's easy to do, but it's certainly repeatable and not difficult. Anything else?